Hello everyone. So today's video is about how the inference work with the GPT models. So we are going to dive deeply into it, understanding each blocks in the transformer model or the GPT model, and knows the main parts that makes the inference for us or make the predicting of the next token. So how does LLM do inference? In today's short video, we will consider the model's weights that have been pre-trained, and we will use inference process to generate the output or the next token. So for simplicity, I am going to explain the NanoGPT model, which is with 85,000 parameters only, powered by Carpathic code in his series 0 to Hero. And also I am going to use some LLM visualization, which is a 3D interactive model for a GPT style. And also it's powered by Brendan Bycroft, which is a great 3D interactive as we gonna see in this video. Okay, so this is mainly the transformer or the decoder only transformer that we are using for the inference or for generating the outputs. So how to predict next tokens words? We pass through different layers in the decoder only transformer. We have the embeddings layer, we have different norm layers, and also we have the self-attention, which is the main block here in the transformer. We do also some projections and we pass it to the MLB or the feed-forward neural network. And this is mainly the transformer. Then we have the softmax where we get the probabilities of the words or the vocab and get the outputs. So today's we are going to do simple example. So considering this a sequence of 6 letters C, B, A, B, B, C, and each of these letters actually a token. We can consider it as a token, and set of the model's different tokens make up its vocabulary. Each token we will assign to it a 0, 1, 2, which is a unique ID. We can call it token index, we can call it input IDs, which will be the input for the model, the way that the model understands it. So also in the visualization bars, we are going to see some green cells, which are the representing the number, and also we are going to see the blue ones, which are the weights. Each number in the sequence will get turned into a 48 element vectors that is defined by the model, and we call this an embedding. The embedding will pass through the model series of layers for the transformers, as we are going to see, before reaching to the bottom where is the output. So the output will be a prediction of the next token given by probabilities, and the next token is going to be like A, B, or C, and the model will be pretty sure that it's going to be A. Why A? What is the probability? How we get to this point? That's what we are going to see. Let's use the token index, for example, B equal to 1, the second one, for example, and select the second column of the token embedding matrix on the left, for example. Okay, so note we are using the 0 base indexes. Now we need to ensure that this is the input IDs for each letter, okay? And the indexes here is 0, 1, 2, 3, 4, 5, okay? So this is just for understanding how we are going to name and to map these numbers. And we will take this token embedding along with position embedding to create our input embeddings. So let's move up the visualization. This is the NanoGPT model. Now if we can see, this is the fourth one, taking from the tokens, the fourth token, which is index 3, starting from 0, 1, 2, 3. And we will do now both the position, and the token embeddings are learned during the training. This is important to say. Now we have these two columns, vector, and we simply will add them together to produce another column vector, as I have said. So the process will go like this, taking the token embedding and the position embeddings, and then adding them up, ending up with the input embedding that we will use later for the model. We will run the same process for all of the tokens in the input sequence, creating a set of vectors, okay, for both the token values and their positions. So by this, adding them up, ending up with the input embedding that we are going to use it as the input of the model. The next layer in this process is the layer norm, and we have three here. So we have a layer norm or a normalization step for the attention. We have one for the feed-forward network, and we have one for producing the outputs. And this is go through mainly normalizing the data and adapted it to be work with the softmax function that we will see at the end, which we want to ensure all the probabilities we get is positive and between 0 and 1. So the input embedding matrix from the previous section that we have got is the input of the first transformer block, which is the layer norm. Now, this operation normalizes the value in each column of the matrix in a separate way. And normalization, as we know in deep neural networks, helps to improve the stability of the model during the training process. So we can regard each column separately. And now in this example or visualization, we are going to focus on the fourth column, which is t equal 3. So let's see the process now, how it's going to be. Note here, we have the bias, we have the weight, okay, and we using, of course, some aggregation functions like the mean and the standard deviation to create this, to convert the input embeddings that we got from previous step into an layer norm, or let's say normalized inputs embeddings. So the goal is to make the average value in the column equal to 0 and the standard deviation is 1. To do this, we find both of these mean and standard deviation, and then for the column, of course, and then subtract the average and divide by the standard deviation. Now we have also two functions we are going to use, which is the variance one and the average one, ex and var x, for the variance. The variance is simply the standard deviation squared. And also we will have a epsilon term that's to prevent the division by 0. So let's see the first functions, how it's performed, to understand more. Okay, so here we go. The input embeddings goes to the layer, and we start from the fourth column. This is the example, and here we go. We have the ex, we will compute it, and we have the variance and the epsilon as I have described. We can compute and store the values in our aggregation layer, since we are applying them to all values in a column. Okay. Now we will see the whole function. The normalized value, multiply each element in the column by the learned weights and also by the bias, and resulting in our normalized values. Okay, and we run the operation in each column of the input embedding matrix to result in the normalized input embedding to be ready for the self-attention layer. That's it for the normalization step. We can move now to the heart of the transformer, or of the GPT. This is the phase where the columns in our input embeddings talk to each other. So the attention layer is made up of several hits, as we know. It's different from each GPT model. For example, GPT-2 or GPT 3.5, each has a different number of hits. First step is to produce the important three vectors of each of the T columns that we have, okay, from the normalized input embeddings. And these vectors actually are QKV, which are the query vector, the key vector, and the value vector. Okay, let's see now. We are passing to the transformer, the first layer. Here we go, the hits 1, hit 1, hit 2. Now we are focusing on 1, and here we go. We have the Q vector, the K vector, and the V vector. Okay, here is the input, the normalized one, the normalized input embeddings, and we have some bias for each vector, and we have the weights that are trained on when we train the model, the GPT model. We have here some kind of a projection, and this is the first thing that we need to understand, and here everything goes actually from getting from the input embedding reaching to the output. Okay, so to produce one of these vectors, we perform simply a matrix vector multiplication, and also we add the bias. So each output cell is some linear combination of the input vector. Okay, so for example, let's see the query vector. This is done by dot products between a row of the Q weight matrix and a column of the input matrix. Okay. So now the dot product operation here is very important. We pair each element from the first vector with the corresponding element in the second vector. Now we will see, mapping them. Then we will do the multiplication. So we multiply the pairs together and then add the results up. Okay, here we go. We add all the results up. And this is a very general and a simple way of ensuring each output element can be influenced by all the elements in the input vector, where that influence is determined by the weights that we have. Okay, let's see now the weights. The bias is added and we put it here. Okay, we repeat this operation for each output cell in the QK value, the two products. Okay. Okay, now let's consider another example just for simplicity. So what do we do with our query key value vectors? The naming gives a hint. So the key and the value are actually a dictionary, which is, we call it a lookup table, with keys mapping to values. Then the query is what we use to look up the value. So now in case of, let's focus here. In case of self-attention, instead of returning a single entry, no, we return some weighted combination of the entries. Okay, so we have weight 0, weight 1, weight 2. To find the weighting, we take a dot product between the Q vector and each of the key vectors. Okay, so one Q vector and multiple key vectors, we make a dot product, and then we normalize the weighted, okay? And then the weighting, we normalize it, and finally, we are using it to multiply with the corresponding V vector, and then then we add all the values up. Okay, so this is the idea. So now back to the visualization, resuming it from here. I want you to notice something here. Okay, so we do this. We get the Q vectors, K vectors, V vectors, and now everything is fine. Now we will have this K vector. First of all, we are just doing the dot product between the query and the keys of each of the previous columns with one fixed of the query. So we are going to do the following. We pass through and we end up with these values in the attention matrix. The dot products now is a way of measuring the similarity, okay, between the two vectors, as we do, for example, in another example, in cosine similarity, when we have two embeddings representing a sentence, and we want to see how similar is this to the second one. We do the cosine similarity, and we end up with a value in case it is positive and close to 1. It is very similar, and if it is negative or 0, so it is not similar. Different sentences with different meanings. So here's the same concept. The idea of using the query against past keys makes the self-attention causal. It doesn't know tokens cannot see actually into the future, and that's we call it the masking part. Another element is that after we take the two products, if you can notice here, we divide by the square roots of A, which is the length here of the query K vectors. The scaling is done to prevent large values from dominating the normalization or the softmax later on. Okay, so finally, let's see now the process. Finally, we can produce the output vector from our column, and we look at the T5, okay, T5 here, row for the normalized self-attention matrix from each element. So we multiply the corresponding vector. Now is the term for the value or the V vector. So we multiply the corresponding vector of the other columns element-wise. And we add these up to produce the output vector, as we can see. So now the output vectors will be denominated by V vectors from columns that have high scores only. So now we know this process is done using one query with the key values, and we end up with the values one, and they are adding up to our output. We can do the process now for the whole columns, or for all columns, and getting the vector outputs. To combine the output vectors from each head, we simply stack them on the top of each other. Okay? So now we have 3. Each of them has a length of 16, ending up to only one vector with a length of C equal to 48. Now, it's important to note that in GPT, the length of the vectors within a head, which is we call it A, equal to 16, is equal to the C, we call it the channel, divided by the number of heads. So now, as we have A equal to 16, and we end up with a matrix with length of 48, we can conclude that the GPT we are using has 3 heads. So this ensures that when we stack them back together, we can get the original length. From here, we perform what we call the projection to get the output of the layer, and this is a very simple matrix vector multiplication on a per column basis with also a bias added. So let's see the function. Okay. So now we have the output of the self-attention layer. Instead of passing the output directly to the next phase, we will add what we call it element-wise to the input embeddings. So it will perform this by simply adding the inputs with the attention outputs. With this, we have the results of the self-attention, and we can pass it to the next layer in the transformation, in the transformer, which is the MLB or the feed-forward network. So this is the next half of the transformer. Now we have each of our C, which is 48 length, as we can see here. They are, as I said, independent. A linear transformation with a bias added here to a vector of the length of 4 of C. And also we have an activation function. So this is mainly the main part in the feed forward. I am passing it to this visualization now. So first we run through the matrix vector multiplication with the bias added to expand our vector. Let's see now. We have the bias, we have the activation function. I am going to explain a little bit. Okay, so now we can see how it passes with the layer node. And then we are using this activation function. So when we apply the activation function, and this is called a GLO activation function, similar to ReLO, but the key part of any neural network is the activation function. And we are doing this to produce or to introduce some nonlinearity into the model. So the specific function used here, as I said, is GLO, and it is like the ReLO function, which is take the computed the max, 0, and x. But it has a smooth curve, as we can see, not like in the ReLO, which is a sharp corner. So we are doing this process for the activation function. And after that, after we got the result, we do another projection, okay? So as we have explained in the self-attention and it is projection, we are doing the same here actually. We project the vector back down to length C with another matrix multiplication, and we add the bias. This will be the output of the MLB, element-wise. We can repeat the whole process for all the columns in our inputs after we got the MLB resident. Okay, we can see now we are doing everything for all the columns. Okay, so this is pretty much the transformer. This is actually the main thing of any GPT model, the last layer, which is the output layer. As I have explained, the soft operation that we use in the self-attention are used here at the end of the model. The goal is to take a vector and normalize it, or normalize its values actually, so that they sum to 1. And all the values, of course, will be between 0 and 1. But it is actually, in our case, in the GPT model, it is not simply divided by the sum. No, we actually taking each input value, its first exponential. So it will be exponentiated. So this is have the effect making all the values positive. So once we have a vector of our exponential values, we can then divide each value by the sum, as we can see, by the sum of all the values. And this will ensure the sum of the value is 1. Okay? And this will provide a probability distribution over the original values. Okay? Also, there are many details about taking the max, subtracting the max, and then of the exponential values and dividing by the sum of it. So this is important to see all the details behind it. So feel free to go and investigate more about the softmax. But the main job what it's doing is actually this, to ensuring the positive values, to have a sum of 1, and then we can we can choose the next token with the highest probability. The main process of producing the output. So this is a recap for the tokens, and then generating the input embedding using the position embedding, the token embedding that we have, and we calculating actually the key VQ values and getting on the projection and getting the outputs. And we are doing in here the MLB part with the activation function, and when do the other things that I have explained for different layers. Now we have our logits that we are going to calculate the softmax and getting the next token. So this is pretty much the concept of the inference of large language model. Hope you understand better with these visualizations and explanations. Thanks for listening.